In the present work, we study the deconfining phase transition from a pionic gas to a color singlet quark-gluon plasma with two quark flavors by using a phenomenological thermodynamic approach with two-phase equations of state. For this, we calculate the partition function of the QGP with the color singletness requirement. We perform a projection onto the singlet's color representation using the density of states determined by the multiple reflection expansion approximation, including a curvature and an area term additionally to the volume. Such a density of states is given by this expression, and we notice that we consider massless up and down quarks, and then in this case the area term is vanishing. The partition function of such a QGP is then given as follows. We use also a phenomenological model assuming the coexistence of the hadronic gas of pions and the QGP phases in a finite volume V, and a parameter H is defined to characterize the fractional hadronic volume. Then we can calculate the mean value of any thermodynamical quantity knowing the individual partition functions of the two phases. Thus, we examine the behavior of the order parameter, which is nothing but the mean value of the hadronic volume fraction with and without the contribution of the curvature term. This figure shows that there is a shift of the curves with the curvature contribution to high temperatures. Also, it is clear that this shift is more considerable in small volumes, while it is reduced with increasing volume. By examining the curvature coefficients, we see that the two are negative, and this is exactly what causes this shift of the transition temperature to lower values. The variations of this shift of the transition temperature with the volume are described by a power law of this form, characterized by a scaling exponent lambda. We determined this scaling exponent by a numerical finite size scaling analysis, and we find a value of 0.732. This is to be compared to the value of lambda obtained previously in the case of the contribution of the volume term only, which was 0.876. So, including curvature term additionally to the volume 1 in the density of states has led to a similar behavior of physical quantities characterizing the deconfining phase transition, as in the presence of the volume term only, with a slight shift in the effective transition temperature. This shift is considerable in small volumes, while it is reduced when the volume increases. Also, the contribution of the curvature term lowers the value of the shift scaling exponent. Thank you for your attention.